welcome everyone to the sixth meeting of our Python data science study group. And this time we're going to be going over correlation and working through that fun stuff. I'm Michael Porter with Muddy Boots Code, as we've mentioned before. Joining me today is Nathan Smith, our resident data scientist with Love Every. I always mess it up.
Love Every.
Love Every. That's it. Absolutely. So Love Every, and we have Jeremy McGraw with us as well today. I said again, we are going to be covering correlation and its measures and things like that. So again, chapter 1 here is exploratory data analysis. And so, like it says here, in many projects, what you're going to be trying to figure out, before we were looking at probability, and now we're looking at correlation. And correlation is basically just a measure of if something is connected, and if so, how much and in what way, negatively, positively, etc. Is that pretty concise capture of that? Because I've got two children that they can't get the correlation between, if I do X, I get Y, and then every day it seems like a mystery about how we do the same things over and over and end up with the same outcomes. And I've tried to explain this concept to them, and I fail all the time.
I think that's a good summary of what's going on.
Classic causation correlation.
Yeah, absolutely. I'm like, this activity results in a consequence. This is how this works. This is where we're at. So, I've kind of went through here before the meeting and highlighted some stuff for myself, and hopefully it helps. But basically, just like it says there, we're looking at a correlation among predictors, between predictors and a target variable. We have variables X and Y, each of that are measured data, and they're positively correlated if high values of X go with high values of Y, and low values of X go with low values of Y. That makes those things negatively correlated. Try to move my little screen sharing thing out of the way here because it's in my way of reading. So again, vice versa, there we are, variables are negatively correlated. So key terms for correlation are correlation coefficient. It's a metric that we use to measure the extent to which numeric variables are associated with one another, and that ranges from -1 to +1. We're able to use a correlation matrix, which is a table where the variables are shown on both rows and columns, and the cell values are the correlation between the variables. And then another method, I think, which is actually like one of the original kind of measures and ways that correlation was shown is with a scatter plot, where we do make a mark on the X and Y axis of values and see if they correlate or whatever. I think I remember reading who's the guy? John Galton. He's sadly the father of eugenics, but also was a relative of Darwin. And he was one of the first people that got involved in correlation, and I think he was the one that actually termed the phrase regression to the mean and all that kind of stuff to describe that. Just because necessarily two things, like if you have two people that are two very, very tall parents and they continue to have children, the children will not necessarily be taller than their parents. They'll probably regress to the mean or stay at the same height. So that's my historical tidbit that I remember about reading where scatter plots came in. So anyway, so we're going to look at this. Consider these two variables perfectly correlated in the sense that each goes from low to high. So variable 1, correlates variable 2 is 4. Variable 2 is goes up to 5. 3 goes up to 6. So here they are, perfectly correlated. They go from low to high, and the vector sum of that product is 32. And now if we shuffle them, not like sounds from the machine there, will never be higher than 32 because that set of variables can't change. Like it's not gonna, they're not increasing, they're not decreasing. They're always going to add up to the same vector there. This idea relates to the resampling based estimate. We say permutation tests, which we're not going to go follow right this second. But values produced by this metric, though, are not that meaningful except by reference to the resampling distribution. In that case, what I'm taking away from that is that, you can shuffle those values, and that doesn't necessarily change what we're getting, but you take another distribution, and you're going to get a better picture of that.
Yeah, so I mean, when those two vectors are perfectly correlated, the highest two values in each vector are matched up, and then the second highest two values are matched up, and then the lowest two values are matched up. So when I multiply the highest two values, I get the biggest possible bang for my buck because that's the highest number in both vectors, and then it continues on down. And so if I shuffled them, I'd be multiplying the highest one times not the highest one in the other vector, and so my product is going to be lower. And when I sum them all up, it's going to end up lower than in this optimal arrangement where I've got the highest with the highest and then the next highest, and on down. So if I had shuffled them in a different way, that would give me a different permutation of the numbers in the vector, and it would give me a lower number back. And so this is the highest possible combination, the most closely correlated that they could be for the values that are in those vectors.
Sure. So there we are. Like I said, that's not necessarily the best way to do that there. And so, like I said, it goes on to tell us that something more useful is this standardized variant, this correlation coefficient, which gives us an estimate of the correlation between two variables that's always lies on the same scale. Again, we're looking at our equation there on how we're going to get it and all that kind of stuff like that. And again, we're dividing that by n minus 1 instead of n. And we've gone over that before in a previous video about degrees of freedom and why n or n minus 1 is sufficient for what we're doing or what we're not doing. If you want to go back and look at that, I can go ahead and do that or whatever else. One of these days I'll figure out YouTube and I'll put like a little pop-up or something that that goes back
awesome.
and references. Yeah. Probably needs to live in my skill set somewhere since I'm making YouTube videos now. But check that out for more details. If you're following along in the book, you can go ahead and click on the link and follow it back there. The correlation coefficient always lies between +1, which is perfect positive correlation, and -1, perfect negative correlation, and 0, of course, indicates that there is no correlation at all, which makes it a lot easier and a lot faster to go ahead and snatch your correlation up. Hey, it's positive, we're in there. It's negative, we're negative, and then it's again 0, it's not. And so you can go ahead and as it gets closer out to 1, you're closer to 100% either way. So that makes a pretty good sense to me. Variables kind of association is not linear, in which case the correlation coefficient may not be a useful metric. The example that they provide is taxes, whereas as taxes are at 0, the revenue, and you go up for a certain range, revenue increases. But as we get closer to 100% tax rate, that number drops off sharply because all of a sudden people start learning to avoid taxation at that rate because nobody wants to get taxed at that rate. And so that correlation coefficient might not be very useful to us. So one of the ways that they present these coefficient correlations is in this correlation matrix, which it shows the correlation between the daily, in this particular table that we're going to look at, our stock prices and correlations in regards there. So we have some data on telecommunication stocks, and we have Verizon and AT&T, which you would kind of expect that they would be correlated, two different telecommunications companies, that their stock will be correlated somehow or another. And then we have a infrastructure company, which has the lowest correlation. So it says on here, note the diagonal ones right across the middle there. And then again, the correlations as they come across for what they are.
And you see the symmetry of that type of a layout too. So sometimes you only need to show like the bottom half triangle of it or the top half triangle because it's telling you the same information on both sides.
Mm-hmm. Yeah, it's like in that form, it's kind of weird to look at. You know, it's like I said, the symmetry of it doesn't necessarily lend itself to like an immediate good picture as far as that goes, or at least not to me anyway. That for me would be a hard visual to connect dots to. So a table of correlations like table 1.7 is commonly plotted to visualize the relationships between multiple variables. And then I said that they have some R and some Python examples, which we could probably, come on, Colonel. All right, we got it. We restarted. Does that mean we have to rerun our stuff? Let's see.
Yeah, I probably have to re-import your libraries.
So let's re-import our libraries. Let's get our data. Let's get our CSVs. All right. So correlation. So let's go ahead and bring in our S&P tables. And then this is going to give us that same table that, well, hold on. That's what I was talking about. I want to run my mouth off here real fast. Yeah, table 1.7. So it's got the same telecommunication symbols. So I guess here's Verizon that we were looking at. There's that infrastructure company, but it's not quite broken down the same as the other one there. This is just looks like the raw data.
Yeah, I think those are the daily values, daily change.
And then going in, we're snatching our sector and ETF symbols. And then we are, in this particular case, it's showing it as a heat map. That's what we're getting to look at here, is that there's so many columns and numbers in that table that correlation matrix, with, like we said before, it's kind of cumbersome. Like you're just seeing the one, you know, the ones right across the middle and the correlation.
I like that. I like that visualization better than the one in the book.
Mm-hmm.
I feel
I
like
agree.
the thickness of those shapes is too hard to discern versus the shading.
Absolutely. So we can see, you know, I said you've got your, you know, your middle values there across, and then, you know, as we get closer to ones and then negative ones, and yeah, I like that quite a bit better than I like the correlation matrix that heat map makes that quite a bit easier to read and look at, and makes a better picture. So for color, grayscale images is used in books, need to visualize the direction as well. So this is so there's another way to do it where we're actually doing the okay, that's fine. This is just a warning that they're going to deprecate something.
Yeah.
So that they're doing this in a book, and then they're doing this in ellipses so that you can do it in grayscale if you needed, and provide the same information that we did there in that heat map. So go back in here, kind of skip past that little code example there. So we got that same graph in Python with no implementation, and then we saw the ellipses and everything that are showing, you know, the orientation of those ellipses is showing how correlated they are.
You know, this kind of information is interesting just by itself to understand what things are correlated. But then if you're preparing to use these as features in a regression model of some type, you don't want to put in features that are too highly correlated, either positively or negatively, because it's basically telling you what you already knew. So I don't need the same information in my model twice. If these two things are really highly correlated, just give me one of them, because I already know what the other one is going to be if they're almost exactly lining up. So sometimes that's called multicollinearity. I'm sure we'll get into that later on in the book. But when you hear about multicollinearity, that means that you're trying to put features into your model that are too closely correlated with each other. So the second feature isn't giving you any new information that you didn't already know.
Mm-hmm. Well, and then and when you're doing something like, like I said, building a model, doing machine learning, or doing, any of that kind of stuff, those resources are pretty precious. And, that's not something you want to duplicate, that effort and all that kind of stuff like that.
Right, and especially hurts in interpretability. When trying to figure out which features are driving the model. If you've got essentially duplicated features in there, then the effects of one feature kind of get mixed up with the effect of the other, and maybe neither one of them shows as important as they really should.
Gotcha. So here we are again. Said, these ellipses are, indicating the strength of the association. Thinner and darker ellipses to correspond to stronger relationships. So it's a pretty neat way to lay it out, and definitely better than that the coefficient matrix that we were looking at previously. Select the mean and standard deviation. The correlation coefficient is sensitive to outliers in the data. Like we talked about before, if the vast majority of your data is in that, what was it, the quatraile that we were looking at, the
Box plot?
I can't remember what it was.
The interquartile range?
Yeah, the interquartile range. So if most of your data is in the interquartile range, you don't want to worry too much about the outliers in this situation. And that's something that this type of data can still give you, or those kind of outliers. And so it talks about that there are, a number of software packages and stuff like with R that give you a more robust computation of correlation. And, you can go in here and look at all these different other correlation estimates, the Spearman's rho or Kendall's tau. And, these are based on ranks of data. And since they work with ranks and values, the estimates are more robust and can handle certain types of like nonlinearities. But they say data scientists generally stick to Pearson's correlation coefficient and its robust alternatives. The appeal of rank-based estimation is mostly for smaller data sets and specific hypothesis tests. So maybe, Nathan, you can kind of like, what exactly is the Pearson's correlation coefficient?
That's the one when people talk about things being correlated, that's the one they usually mean. So
the one that they talk about.
Yeah, exactly. The one they've described earlier in the book is Pearson's, and that's the one that is generally meant when people say things are correlated or talk about the correlation coefficient. They're talking about the Pearson.
Okay, well, I'm going to give them a book send for that, because they didn't say call it the Pearson's correlation coefficient. They said if it was correlated. So, okay, maybe stack that in a little earlier, guys. Next time, it'll go in your notes. I'm sure they're watching these videos and just
on the edge of their seats,
wringing their hands, gnashing their teeth every time we go through their books here. So there we are. That Pearson's correlation coefficient, and then I said the ways that you can go ahead and calculate that to make it more robust and get rid of outliers and things like that. So again, we're talking about scatter plots, and this is this has been one of the original ways to visualize the relationships between these measured data sets. You just plot these points on an X and a Y, and you look for things that gather, and you look for things that match, and these are, like I said, the original correlation measures and stuff like that, and what people used to do. And so what it talks about here is of course, our code examples, which we'll go to here in just a second. But one of the things that this covers pretty good is like, are very well in the book, is that the scatter plots are great until you get to a point where like your scatter plot like density is overwhelming, right? Where you have so many data points and so much stuff going on here that it would be hard to snatch out some meaningful data out of that. Like, everything's in one group and one whatever else, but then how do we separate meaningful groups out of this? It talks about in here that you can then go ahead and start sorting values out, making some values like transparent, or looking at different measures, different whatever else, to kind of narrow your scatter plot down and get it to stuff that's actually useful information. So we'll just say same thing here. We'll just run their code. So this is the socks, and then we get our scatter plot here at visualization. And then what they show here as we go down is that they can looks like they are doing anything that's less than 0.5 correlated, that they're actually making those dots like transparent or see-through.
Right. So this is just the level of transparency.
Greater than, yeah.
So every dot is like 50% see-through, and so then when you stack two dots on each other, it becomes more solid.
Okay.
So that just gives you a little bit of way to kind of peer through in the center of that big cloud, that where they're overlapping, you can sort of see both points.
Okay. That makes more sense than what I was thinking. That's just the first time I've looked at this.
So if you change that to a 0.3, they're just going to get lighter.
Right. So it allows you kind of to see that density better, like where they're actually overlapping.
Yeah.
Okay. Makes a good size. Let's make it bigger too while we're at it. Hopefully we can see it better.
Yeah, that's another way to spread them out.
Yeah. So get a better picture that way.
Yep.
I guess if we felt like it, we could also change colors and do things of that nature, but
exactly.
Get even more. I don't know, let's just for the hell of it, play with it a little bit. It's not much of a difference there.
We changed the axis there.
What's that?
We changed our axis to blue instead of gray.
Just looking the wrong thing. So this is, that's the X and Y axis line. Okay, I see what you're saying.
Yep. It's probably.
We change the label colors? Do they take a?
That's the.
Sorry, not the label, the actual dot is what I'm talking about.
Yeah, I think if you go inside the plot, inside the scatter function there, yep, right after the alpha, and just put a color equals red or something like that. Maybe as a string. Yeah.
Okay.
There we go.
I don't know, just fun, just stuff to play with and look at.
Yep.
I've got to mess around with that some more. I've been doing all of my stuff here lately with like React and junk and different ways to do that. But that's, like I said, again, scatter plot. And then now we have a better way to tell, hey, this is correlated, not correlated, and makes it a cleaner picture.
Yeah. So we're using matplotlib, and it's wrapped inside of a convenience function from pandas. But if you wanted to know more about how to tweak this picture to make it even more beautiful, you would just go look in the matplotlib documentation. But the object, the telecom object there, is a pandas data frame that we're calling this from. So you can look either place in the pandas documentation for their plot method, but to get to the finer detail underneath it, the plot method is actually calling matplotlib. So that's where you can go find more clues to different options.
Okay. Yeah, absolutely. Because I would want like the different, I would want the different values to like be different colors. I would do all sorts of stuff because I get crazy.
Yeah.
So again, that we're looking at there, that the key ideas when we're looking at correlation the Pearson correlation coefficient, not just the correlation coefficient, because that later on they'll throw that at you and then want you to know who Pearson is and why it's his correlation coefficient. Measures the extent of which two paired variables are associated with one another. And then said when we have high values of V1 go with high values of V2, these are positively associated. High values of V1 go with low values of V2, then these values are negatively associated. That correlation coefficient is a standard metric, so we always range from -1 for perfect negative correlation and +1 for perfect positive correlation. And then a correlation coefficient of 0 indicates no correlation, but also that just may happen. That could be random. That could just say, hey, this was 0, but that doesn't necessarily mean that there is actual no correlation. Just like real life. Some days it does everything you're supposed to do, and then some days you strike out, and that correlation thing doesn't work too well for us.
You have like using correlation for like generating additional questions to ask about the data. So for example, I'd interviewed for a job once and they wanted to help coming up with a way to rate all of their insurance agents. And they gave me a number of categories, like how many leads they follow up on, or how many applications they close. And there were two different people that had two different arguments. And one person was saying, well, we should let the agents go through as many leads as they can to try to increase how many applications they close. And the other guy was like, no, I think we should limit them to a certain number of of leads to pursue. And so when I looked at the correlations, it was actually negative. The success rate of closing an application was actually negatively correlated with the number of leads they did. And so then based on that, I started kind of looking at trying to assume why that was. And so one of the things I had posed to them was maybe the people that are going through more lead count or going through more leads are they're less successful. So maybe they're trying to rush to get, like, oh, that one didn't work. I wasn't able to close that one. So now I'm trying to get through another one. So they feel rushed, they feel pressured. And then when they actually, connected the names, like the IDs to the actual names of the people that ended up that, like, the people that were less skilled were using more leads because they weren't they weren't as good as closing. And then the people that were actually closing were spending more time, but then actually making sure that they closed the application. So it was one of those, it was kind of not what they were expecting to see, but actually then looking at the correlations between their success rate and the daily lead count kind of showed that, well, maybe you should kind of limit it, or maybe these people need some more coaching on how they're approaching it. So I found that sometimes it can be useful for kind of teasing out additional questions that can be asked and looked into.
Absolutely.
No, that's great, because like I said, that you have those people. They're like, oh yeah, they're talking to more people, they're doing a better job, and like, oh well, absolutely, actually they're being less thorough or less successful because they're not actually putting in the time.
Yeah, exactly.
Yeah. No, that's great. I said, and that's the thing about data science statistics is we're fighting our natural inclinations as human beings to associate meaning with things that don't actually have any meaning, or see patterns where we don't actually have any patterns that exist. Mm-hmm. Well, that puts us in here at about 30 minutes on this video, so I think that's probably pretty good. I'm going to go ahead and say we will stop here today. So again, this thing gives you, as further reading, statistics, and has an excellent discussion on correlation, it says. So I'll take their word for it. I haven't read it, so we'll do that. We'll go ahead and pause. And like I said, in our next meeting, we will be exploring 2 or more variables. We've been looking at the univariate analysis stuff, and so now after this we'll go into the more in-depth stuff there. But hope everybody had a good night. Thank y'all very much for being here as always.
Right.
I just threw something fun in the chat.
Yeah, I saw that.
You haven't seen this page before, but we always talk about how correlation is not the same thing as causation, and things can be correlated for no particular reason at all. And this guy has made some interesting patterns of things that happen to be correlated in time, but they really don't bear any true relationship to each other. So just something to keep in mind, that correlation and causation are not the same thing.
Yeah,
Absolutely.
Another interesting thing to pursue is something to like find correlations that suggest something they don't actually mean.
Let me hop on the share screen real fast. Make sure to show that. So yeah, here we are looking at spurious correlations. So I like it. Now it's a ridiculous book. I love it.
Yeah, like that cheese consumption. The number of people died by becoming tangled.
The number of suicides by hanging and the U.S. spending on science, very well correlated. That's amazing. I would love to see what somebody argue that. So hey, look, every dollar we spend on science kills another human being. Like they just jump into a noose every time. Yeah.
Just have a politician whose all of his opinions are based on poor spurious correlations.
Oh man,
exactly.
That's amazing. I love it. Number of people who drown in films Nicolas Cage appeared in.
Surprised the number of people who died by becoming tangled in their bed sheets. That seems like I think that would be pretty rare, but
this is awesome. Yeah, there's 2 films, 209 drownings, 2 films, 102 drownings. That's you just gotta love that. You gotta love someone who took the time out and built this and thought about these things. That's just amazing.
Exactly. Yeah, just gathering the underlying data.
Yeah, he's got
must have taken some effort
related to cheese and dairy products. He's onto something.
It had to have just like done something that like, okay, if the graph is gonna look this, if a correlation measure is this on the graph, I want to see what it looks like, and then look what the 2 data sets are. That's great. Well, thanks for sharing that, Nathan. That's awesome.
Yeah,
I'm gonna spend some time looking at that after this deal. We'll check that out. But all right, thank y'all very much. Again, that was our run there on correlation, and so next week we'll be talking about the multivariate or multivariable stuff coming up, and
I'll wrap up our chapter.
Absolutely, we'll wrap up chapter 1. That'll be 6 meetings for the chapter, so that's not terrible. Making pretty good headway. So once this recording is over, I will get it up on our site, add it to YouTube, and tweet about it, and then get all the excited people excited and get it done. Right. Thank y'all very much. Have a good night.
Yeah, sounds good.
Yeah.
Good night. Take care.